Hi guys. In this video we're going to be going through the topic of critical path analysis. This is the second part of networks in the syllabus where we're looking more on efficiencies and real-world applications of networks. So first of all, let's go through the syllabus bullet points. So construct a network to represent the duration and independencies of activities that must be completed during a particular project. So this is where we're talking about like the predecessors of each activity and how they all link with each other and how we're going to create a network with it. So given the activity chart, we prepare the network diagram and use critical path analysis to determine the minimum time for a project to be completed. And this is the main thing I would say, where we're talking about the earliest starting time and the latest starting time, so the EST and the LST for each activity, and this is with our forward and backward scanning as we see there. And understand that the EST for an activity could be 0, and in what circumstances it could be greater than 0. So the earliest starting time, if the earliest starting time is 0, that means it's at the start, and there has no other predecessors. Calculating the float times of all the non-critical activities. You could actually technically you can find the float time of any activity, and of course non-critical means that the float time is greater than 0, because the way that we find the float time, of course, is the latest starting time minus the earliest starting time. And so everything that has a float time of 0 is referred to as a critical activity. So understand what is meant by a critical path. Well, what we're talking about there is once we've created our network, there's going to be some kind of path where the float times of each of those activities are going to be 0. Therefore, they're all critical activities. So there's going to be one path, or at least one path, going from the start to the finish where all the float times of those activities are 0. And use, so locating the critical paths. And from that, we also have a few network flow problems, mostly including the maximum flow min-cut theorem, which is where we're talking about, you keep looking at different cuts within the network, and whatever you find the smallest cut capacity is the maximum flow, because you can't exceed that smallest cut. And that's kind of like a whole series of lessons in itself. So if you need to learn more about that, I'd suggest you refer back to your notes or look at other videos or your textbook. So going from here, nothing on the reference sheet or formulas really here. The only formula you really need to know is the float time is the latest starting time minus the earliest starting time, which is quite easy to remember. Everything else is really just a process in this topic. And so this topic, as you see here, this topic has only been in the HSC for 2 years as of this video. So it's hard for us to know exactly what's asked, but when you look at past trial papers and past HSC papers, the main things that are asked are, doing your forward scanning and your backward scanning to find those important values of each activity, and then finding the critical path from that. So let's go through some past questions, and some of these are going to be from trials and some of these are going to be from past HSC, because again, there's not an extreme, lots of HSC questions on this topic just yet. So first of all, this is a multiple choice question. It's question 14, so it's like the second last question in the multiple choice section for this paper, the ACE 2021 paper. So we have this network diagram where we have the source and the sink, and these are all directed activities, or it's a directed network, so they're all going in particular ways, and we need to find the maximum flow. So there is a long process for finding the maximum flow, but I'd suggest you just kind of avoid going through that long process because there's lots of mistakes that you can do along the way. What we want to do here instead is we'll use the max flow min-cut theorem, meaning we're just going to do a bunch of different cuts on this, remembering that a cut is a line that goes through the network such that it's completely separating the source and the sink. So we're going to do lots of cuts and look at the capacities of each of those cuts. And then once we've done, however many we think we need to, we're going to find which one's going to be the smallest capacity. So let's start off with this. If I do a cut here, this is going to be 11 plus 8. So that's 19. So we'll just hold on to that. So it could be that, and we see that 19's there, but let's see if we can find any smaller ones. If we do a cut here, well, that's 1 plus 12 plus 7, so that's 20. So right now 19 is still our biggest. If we do a cut here, so what you want to do when you're going through this, don't just do random cuts and then hope that you're going to find some small number. You should look a bit ahead and look where the biggest numbers are and try to avoid them. So I'm looking at this and I see I'm seeing 11, I'm seeing 10, I'm seeing 12, I'm also seeing 8. So, and then looking at other numbers, we see like 4s and 5s and 2s. So what we should try to do, if we can, is avoid those big numbers. Because if we're adding big numbers, it's probably going to be not be the smallest cut. So let's, if we do this cut, and I've chosen that cut because I'm looking at 5, 2, and 4. So 5 plus 2 is 7, plus 4 is 11. So all of a sudden, we've jumped down from 19 to 11. And that's an important thing that you're doing with these kinds of questions. Look ahead. Don't just do random cuts hoping that one works. And so you might be thinking, well, in this particular question, 11 can't possibly be the answer. It's not an option. So that's also helpful with these multiple choice questions. So let's see if we can get any smaller than 19 or smaller than 11. So if we were to do this cut, let's have a look at that. So first of all, we also need to be remembering that it needs to be starting on the source side and ending on the sink side, which these ones all are. So here we have 2 plus 3, which is 5, plus 2, which is 7, plus 4, which is 11. So we have another cut over 11. But if we look a bit further, we also see a 1. So if we were to do a cut like that, we have now 1 plus 3 is 4, plus 2 is 6, plus 4 is 10. So we have 10. Now we have the smallest number here is 1. So let's see if we can find any other cuts, because 10 is an option, but let's see if we can find an option with 9. And, just having a scan through this didn't work. We've already tried that. Already tried this. And if you just keep looking, there's no possible way that you can make 9. So from this, now that we've done a bunch of different cuts, and we've looked around the place to see if there's any possible ways that we can make it smaller, there isn't. So the answer is 10. So although this might seem like an inefficient or kind of like a guessy kind of way of finding this answer, I think it's also the best way to solve these kinds of questions about maximum flow. Just do a bunch of cuts and find the smallest capacity from those cuts. So that's that question. Looking at this one next. So this is from the PEM paper, question 11. And I've noticed that in past trials and also HSC papers, you're pretty much guaranteed to get at least one question based on critical path analysis. So, we want to be looking out for that. So the directed graph shown below indicates the sequence of activities needed to complete a project. So we have no durations. We only have a bunch of activities. So how many activities have exactly 2 immediate predecessors? So what we were doing is we want to look at all the activities that have 2 things leading into it. So A has no immediate, right away, it can't be A, it can't be B, and it can't be C, because they have no immediate predecessors because they're from the start. So it can't be any of these. It can't be D, because that only has one immediate predecessor. There's only one thing going into the node before D. It also can't be E, all right, because again, there's only one thing going into E, and it can't be F because there's only one thing going into F. All right. Note that we're not talking about things going out of it. We're talking about things going into it. It can't be G. Again, only one thing going into it. It can be I. So I is one of them because we have F going into I, and we also have G going into I. So if we had our activity chart, you would have like the process like I, and then its immediate predecessors would be F and G is what it would look like in our table. H also has 2 immediate predecessors. So we have D going into it and E going into it. And then lastly, we also have J because we have H and I going into it. So there are 3 activities here that have exactly 2 immediate predecessors. So the answer is C. Going into the next page. So similarly here, we have the network shows a series of footbridges. So in these questions, this is from the free response, so QAT 2021. So the network diagram shows a series of footbridges and treetop walks in a national park. The vertices A, B, C, D, E, and F represent 6 platforms. The edges represent the footbridges connecting these platforms, and the numbers on the edges indicate the maximum capacity allowed on the footbridge. So what we're going to do first of all is determine the maximum flow, and again, max flow min cut theorem. So let's just do a bunch of different cuts again and see how we can minimize the number. So this is technically a cut, that's 14. That's also a cut, so that's 14, 14, 14. I'm getting lots of 14s, but again, this is me just randomly putting a bunch of cuts together and hoping that I get a small number. That was me not actually looking ahead. So I got 14, 14, 12, 8, and 6. These are big numbers, but if I look closer, I see 2s and 4s and 3s and 2s. So I should be looking to see if there's a way that I can make these numbers any smaller. So let's start off with the 2. Let's see if I can get into the 4 rather than go into the 12. And then from here, I can either go into the 3 or the 2. Now looking ahead, that 2 is going to have to take me back into the 6. So let's go into this 3 and then just go into this 2. So what I've done here is in this cut, I'm looking for small numbers as I go through. So this is 2 plus 4 is 6 plus 3 is 9 plus 2 is 11. All right. Now that's 1 and that looks pretty good. And in fact, that is going to be the answer. But what you should do is at least spend a couple more minutes thinking, is there a smaller way that I can do this? So let's try this cut, like 2 plus 4 plus 2 plus 6. So 2 plus 4 is 6, plus 2 is 8, plus 6 is 14. So that's another 14. That didn't work. We could try, like, I know, 8 plus 2 plus 3 plus 2. But again, that's going to be too large. And again, the whole process of this, even though it is kind of guess and check, you can make educated guesses by looking at the capacities of each activity or each edge, and then making a good judgment of where you should go. So anyway, after you do a few more cuts, you'll find that 11 is the smallest you could possibly get. So therefore, we can say the maximum flow equals 11 people. All right, you might as well answer in context of the question. So we're saying the numbers on the edges indicate the capacity of people on the thing. So the maximum flow is 11 people. Okay. And then looking at this, a cut is added to the network as shown. What is the capacity of this cut? So we just want to find, the sum of this. Now, the trick to this is not simply just going to be like 8 plus 2 plus 3 plus 5 and that's it. Because what we also need to consider is, are all of these need to be added? Because this is the source and this is the sink. And we've talked about, for it to be added to the cut capacity, we need to only add the ones that start on the source side and end on the sink side. So looking at this cut, first of all, this intersection, it is starting on the source side and ending on the sink side. You are looking at the arrows. So it's going this way. So it is starting on the source side, ending on the sink side. So we are going to add that one. Looking at this one, however, it's going in this direction. And so therefore it's starting on this side of the cut, which is the sink side, and it's ending on the source side. So we don't count that one. And that's an important thing. And that's why this question is being asked, because it's asking you, do you understand when or when to not factor that in? This one, it is starting on the source side, ending on the sink side, and this one is starting on the source side, ending on the sink side. So we're ignoring this one, and then from this, it's going to be 8 plus 3 plus 5. So capacity equals 8 plus 3 plus 5, which equals 16. Apologies if you can hear a bunch of screaming in the background. There's a sport class outside. All right, and this last question, and this is a typical question as well. So this is from ACE 2021, question 32. So we have this activity chart now, and we need to draw a network diagram for it. And this can be quite complicated, and this is definitely something you'd want to cover, because being able to draw these networks is very helpful when it might be asked. And as you see, this 2 could even be 3 marks. So when we're doing this, before we draw anything else, we should think of, first of all, what are going to be our starting activities or activity, and what are going to be our finish activities. So the starting activities are the ones that don't have an immediate predecessor. So A is a starting activity, and there are no other starting activities because that is the only thing without an immediate predecessor. So now what we need to think of are what are going to be the finishing activities. And the things that are finishing activities are the activities that are not an immediate predecessor to anything else. What that means is we need to look at all the letters or all the activities that don't show up in this column. So we see that I isn't in this column, so that means that is going to be a finishing activity. H also isn't in it. G is, so G isn't going to be at the finish. F isn't in this column, and E isn't in this column. So now that means we have one starting activity and 4 finishing activities. So we've figured out what our start and finish are. The other thing we need to identify is, do we need any dummy activities? And remember, the way that we identify any dummy activities is we look at the immediate predecessors and we look to see, are there any activities that share some predecessors but don't share all predecessors. So we see that, for instance, B, C, and E all have the same immediate predecessor A, except they all are just A. None of them are saying like A, B. If one of them did say A, B, then yes, we would need a dummy activity because this one's A and this one's A, B. But because this one is just simply A, no dummy is required. Same for C, C. They're identical, so no dummy activities are required. So now that we've done that, we've identified the start, we've identified the finish, and we've identified any dummy activities. In this case, we don't have any at all. So what we want to do from here is we now need to start drawing that diagram. And this is where it can be quite a bit tricky, and so let's go through it. First of all, we have our starting point, and I would suggest when you're doing these network diagrams, have a starting point, and then we have one activity at the start, so there's our activity A. All right, we have our activity A, and now we're going to have our 4 finishing points. So here's our finishing point, and we're going to have 4 activities going into it. So we have E, F, H, and I. Right, so E, F, H, I. Now, one thing that I will point out right now, and I'm not really giving a good example of this in this video, do this with a pencil, because you might make lots of changes as you're going through. These network diagrams are often quite messy, particularly if you're going to have things crossing over. So I would suggest using a pencil, or even more importantly, what you can do is do your initial draft of the network diagram, maybe on like the back of the reference sheet or something, and then transpose it into the actual working space when you've made it a bit neater. And I'll give you an example of that. So now that we've done this, we now need to start. We've got our start, we've got our finishing points, and now we're going to work our way back up the table. Remember, doing these network diagrams, I think the best way of doing it is starting from the bottom and making your way up. So let's start with activity I. Activity I, its predecessor is G. So we're going to just have I start here, and then G comes out of it, goes into it, okay? So we have G. Now I'm not going to put a dot here yet, and that just gives me a bit of flexibility later on, but I have G going into I. Also, we're going to put, directions on these as well as we go along, because these are directed networks. So we've done I, and you can just tick it off as we go along. Now let's look at H. So the predecessor of H is D. So let's just put a dot here, and then we have activity D going this way. Next we have G, and that is coming, so activity G comes from C. So here's our G, and then C I'm going to work this way. And I'm kind of curving it towards this because I think it's eventually going to go to A, and in fact it does. So I have C, but I'm not going to put a dot on there just yet. As you're creating new activities, I don't suggest you put a dot on the one side because you don't know where that's going to eventually end up. So we have G done. F also comes from C. Now this is where I was suggesting it's always good to do it in pencil or do one draft and then go later, because now I have F and I need it to come from C. So it's actually going to have to go through D, and although that has no actual significance on the network, it just makes things a bit messy because now I kind of got F, like F comes from C, but it just doesn't look great. Anyway, but that is done. Technically it is correct. C happened and then F can happen. Next we have E comes from A. So E is coming from A, which I've already drawn. So that means I can simply just get my E and connect it to the end of A. All right, so we just have like this one long edge going across. That one's done. Now D comes from B. B I haven't drawn yet, so I'm going to put a dot here and then draw that B. Remembering, I don't want to put a dot here because I don't know where that's going to end up, or start rather. Now, C goes to A, as we've already seen. So C is going to A. Cool. B is also going to A. And A, well, we've already done with having saying it was at the start. So we can also write that's the start and that's the finish. And there we go, we've drawn our network. Now, again, like I said, we actually have one of our lines, though, kind of crossing this. And although mathematically there's nothing wrong with this, it might make things a little bit messier later on because we're about to do some forward and backward scanning as well. So if you had a pencil, you might be able to rub this line out and then you could put the line like around here instead, just so nothing's crossing each other. It might just make things a little bit cleaner. So for example, what I did in a previous attempt of this question is I started off by doing my network like this in pencil, and then I found that F is crossing and all that. And then what I could do this maybe on the back of the reference sheet or something, and then I cleaned it up with all these numbers. Note, yes, I've already done the next few questions, but you see that I've got nothing crossing over each other anymore. So these two are saying the same thing, except this one has no crossover. Anyway, going back to this. So now we need to find the earliest starting times and the latest starting times for all activities. Show your answer on your network diagram for part A. So this is where we need to do the forward scanning. So we have A, and what it might be worthwhile doing, first of all, is write the duration for each of these. So this is 5, B is 6, C is 4, D is 2, E is 7, F is 6, G is 1, H is 3, and I is 2. So we've gone out and drawn our durations, and so let's now do this process. So we're going to have like these two boxes next to each activity. So this is our starting one, so of course it's 0, and then we don't have anything for the latest starting time yet. So now let's look at the earliest starting time for C. Well, C comes from A, and we just got this 5, so that's 5. B also comes from A, so the earliest starting time is 5. And E, which is all the way over here, I might even just scribble this out and draw it here. So I've got E7, and that box is 5, and we don't know what's coming up next, okay? I'm also going to write F6 here, okay? So now that we've got this, let's just make our way through. So E goes to the finish. So if I do 5 and then 7, so one of the possibilities for the finish is 12. And we'll go back to that in a second because it's going to be 5 plus 7. So the earliest starting time for the finish could be 12. All right, but we need to think of all the other ways that we can get to the finish. Earliest starting time for D would be, well, we went with 5 and then another 6. So D is 11. And then after D, H is, so D 11 plus 2, so H is 13. And then 13 plus 3 is 16. So another possibility for the finishing time is 16. But again, we need to just wait to see all possible possibilities. Now, looking at F, so F comes from C. So I did my 5 and then another 4. So F is 9. And then 9 plus 6 is 15. So 15 is another possibility. And then lastly, going from looking at G. So G comes from 5 plus 4 is 9. And then 9 plus 1, so I is 10. And then 10 plus 2. Yes, 10 plus 2 is 12 again. So there we have that. So all 4 ways going into the finish now have been factored in. And so the minimum completion time needs to be the biggest of these numbers. Remember, when you have a choice between 2 things, when you're doing your forward scanning, you choose the biggest option, which in this case is 16. So we have 16 here now, and now we need to do the backward scanning. So starting with 16, we're going to subtract, looking at E first of all. So 16 minus 7 is 9. So we have that. And then looking at F, we have 16 minus 6 is 10. Looking at this one, we have 16 minus 2 is 14. And then 14 minus 1 is 13. And then we'll get back to the C in a second. Looking at H, we got 16 minus 3 is 13. 13 minus 2 is 11. 11 minus 6 is 5. And then looking at this one, so we have C and we have 2 things coming out of it. So in this case, we need to choose the smallest one. Like where for forward scanning, when you have more than one option, you choose the biggest one. When you're doing your backward scanning, when you have more than one option, either 10 or 13, you choose the smallest one. So the 10 minus 4 is 6. And then now again, we have for A, we have 3 different options. We can either use 9, 5, or 6. We're going to choose 5 because it's the smallest one. So 5 minus 5 is 0. So we have that now. We've now done the forward scanning and the backward scanning to find the earliest and latest starting times for each of these activities. So now, these last 2 ones are a little bit easier from all this. So what is the critical path of the network? Remember, the critical path is the path made up of all the critical activities. And the critical activities are the ones with a float time of 0. So 0 minus 0 is 0. 5 minus 5 is 0. 11 minus 11 is 0. 13 minus 13 is 0. So our critical activities are A, B, D, H. So our critical path is A, B, D, H. So A, B, D, H. And then lastly, what is the float time for G? Remember, float time is just latest starting time minus earliest starting time. So G is 13 minus 9. So 13 minus 9 equals 4. So those 2 questions are extremely easy once you've done all this. And this is 2 marks, and this 2 marks is a lot easier and quicker to get than these 2 marks or these 2 marks. But that's what happens. As we know, not all marks are created equal in the HSC. Anyway, so hopefully this video has been helpful in explaining a few things about a topic which is completely new to the syllabus and isn't exactly like anything else we do in mathematics. For that reason, it can be a bit trickier, but because it is a new topic, and it is such a focused topic, you're pretty much guaranteed to get at least 1 question on it. Probably got to do with like earliest or like flow times or forward scanning and backward scanning. So you definitely something you want to be comfortable with. Yeah, hopefully this video has been helpful. And if you have any more questions, be sure to ask. Thanks for watching.